Hey guys, hope you're all doing good and welcome to a new video. So today we are going to be talking about the PISO algorithm. Several times during this particular course I've talked about this PISO algorithm, and while setting up cases in Converge you might have seen the term PISO algorithm in multiple locations. So I wanted to talk about what PISO algorithm is and why it's important for you to understand it. So let's start with the Navier-Stokes equation. So here we have the Navier-Stokes equations. And as you all know, Navier-Stokes equation is non-linear. So the term that's non-linear is highlighted in red color. Now remember, your computers are fundamentally linear machines, meaning they are designed to solve linear equations, right? So what you basically do is you use something called as a predictor-corrector method, and you might have guessed what this method does. Since your computers can solve only linear equations, this predictor and corrector method is essentially converting your non-linear system of equations into a linear equation, right? And when you do this, you gain the ability to solve these equations using your computer. So the PISO method, which stands for pressure-implicit with splitting of operator, is essentially a predictor-corrector method which linearizes your equations so that you can get a solution. Now you might have heard of several other methods such as simple, PIMPLE, or any other combinations of these, right? These all fall under the classification of something called as pressure-velocity coupling algorithms. So what does that mean? Well, if you look at our governing equations, right, we have a continuity equation, we have momentum equation, and let's forget energy equation. Assume that we are in the incompressible world. Now, if you think about it, in the momentum equation, you are solving for rate of change of velocity with respect to time, correct? But if you look at the continuity equation, you just have dou u by dou x plus dou v by dou y, which is just, the divergence of velocity, correct? But what about pressure? We don't have an equation for pressure, right? And that is the fundamental problem here. You don't have an equation for pressure. So when you're starting out with your CFD calculations, when you start out with an initial condition for pressure, right, there is no guarantee that the velocity that's computed with that pressure, right? Now remember, in the momentum equation, pressure is on the right hand side. So initially you're guessing that. And with that guess value of pressure, you're getting a guess value for velocity, correct? Now take this velocity and put it back in the continuity equation, which is divergence of velocity vector, which is nothing but divergence of velocity vector. Is that going to be 0? No, it does not have to be, right? Because there is no rule that basically says that this initial value of pressure has to satisfy the continuity equation, right? And this is the problem of pressure velocity coupling, right? And any algorithm that kind of gives a solution to this is called as the pressure velocity coupling algorithm. That's basically it. So how does this all work together? Well, when you're setting up your CFD simulation, you set up the initial pressure, right? If you remember, under regions and initialization, there is an option to choose this. So you have chosen this. Now with this pressure, what you do is you evaluate your momentum equation, right? So your momentum equation is, you have your dou u by dou t terms plus your convective terms. Again, I'm just writing this for 2 dimensions, equal to minus dou p by dou x. And this is where the initial condition is going, plus mu times dou square u by dou x square plus dou square u by dou y square, right? Now once we put our initial conditions here, with this you can calculate a value for velocity, correct? Now this value of velocity is not going to make sense if you take it and if you put it in dou u by dou x plus dou v by dou y, it's not going to be equal to 0, right? So what we have to do is we have to derive an equation which basically helps us get a pressure value which will satisfy the continuity equation. That's it. Now the way this is done is by performing some mathematical manipulation on the momentum equation and then applying the continuity equation so that you get an equation for pressure, and that equation of pressure looks like Laplacian of P is equal to some right hand side. Now this right hand side is going to be a function of u, v and w if it's 3 dimensions, right? You get this elliptic equation. Now the idea is if you're able to solve this elliptic equation for pressure, that pressure can be used to compute a velocity which is guaranteed to satisfy the continuity equation, and that is what you call as a pressure velocity coupling algorithm. Now what happens is you initially start with guess values, right? You have guess values for velocity and you have guess values for pressure also, correct? Now what you can do is with the guess value of pressure, you can compute a guess value of velocity, right? You can call it as u star. Now this u star is not going to satisfy continuity. We all know that. So what we do is we take the Poisson equation and we basically use the star values in our Poisson equation. So we take this and put it in the Poisson equation and we get an intermediary pressure, P star. Now, sometimes this pressure correction can be too much, meaning this corrected pressure can cause instabilities in your solution. So what you can say is, you can say that the corrected pressure is your initial guess pressure plus alpha times P star. Now this alpha is called as a relaxation factor. It can be greater than 1 or it can be less than 1. Typically what you do is you say that this is actually less than 1, and that's why you call it as an under relaxation factor. So that way any changes that this equation is giving you, you are basically using it, but only a portion of it. Now you can take this corrected pressure and you can get a corrected velocity, right? And similarly what you can do is you can use an under relaxation factor for the velocity as well. This is the entire algorithm. Then you might ask, why is there a need for simple, PIMPLE and PISO? Then you might ask, what's the difference between simple, PIMPLE and PISO? Well, the key difference lies in the number of correctors that you're doing and the formulation for the correctors. This is something that we will not be discussing in this course, but the equations are available in any standard finite volume textbook. Basically, the difference between the simple method and PISO method lies in the formulation of the corrector equations. In simple method, certain terms are dropped. In PISO method, those terms are not dropped. That's basically it. If you take up a standard FVM book, you should be able to understand this. So how does the PISO algorithm work in Converge? Say that you're running a transient simulation. You start your time step and you start your PISO iterations. We are not talking about this block because I'll talk about it later, right? So you start your PISO iterations, you solve your momentum equation, and then based on those values of velocity that you have, you solve your pressure, and based on the pressure values that you get, you correct your velocity. This is where your under relaxation factor comes in. Now this PISO loop, and then what you basically do is you check if your PISO has been converged. So for this, you just compare the density values before the PISO and after the PISO, or you compare the pressure values if it's an incompressible flow. Now say that the equations are not converged, then what you do is you solve the equations for density, species, or any other transport equations that you have, and then you update your pressure ratio, solve for pressure, update the velocity, and you keep on doing this process. Now once the PISO is converged, the code is going to check if the strict conserve flag makes sure that the transport equations are solved more tightly, meaning they are solved more closer to the tolerance. So here you're basically solving for density, your species equation, the energy equation, you're again updating the pressure ratio, solving for pressure, and updating the velocity. Right after this PISO and right after strict conserve, you have the second corrector, right? That is the difference in between PISO and simple. In simple, you don't have those additional correctors. All right. So once you do this, that is basically an end of a single PISO loop. Now you can repeat the PISO loop couple of times within a given time step. All right. Now remember, only after these calculations are being done, you solve for your passives and your turbulence parameters. And this is what we call as linearizing, right? Now if you remember from your turbulence lectures, the turbulence parameters depends on the velocity, and the velocity also depends on the turbulence, right? It's coupled. But what you're doing is you're solving only for the velocity components, and after a small delay you're solving the turbulence parameters, right? So now this delay, during which the velocity terms in the nonlinear part and the turbulence part are being held constant, is called as linearizing. All right, I hope that makes sense. And then once you solve for turbulence, that's basically it. You end the time step and then you go to the next time step and you repeat the process. So what are these parameters? Well, if you remember your transport equations, right? Any equation that you have might have a source term. For example, your momentum equation might have a source term, your species equations might have a source term, correct? These sources are updated, right? They are updated based upon the most recent values that are available, right? And then you proceed to calculating the PISO loop. Now, so how does Converge solve the linear equations? Well, it uses some pretty standard algorithms. We use Gauss-Seidel SOR. Now remember, all these methods can be over-relaxed or under-relaxed. So an iterative method is basically for solving a linear system Ax equal to b. The idea here is that x is what you're solving for, correct? And initially you start with a guess value for x, and then you take that guess value and you compute Ax equal to b. Obviously you're not going to get the right answer, right? There's going to be an error. Now based upon this error, you correct your x values. When you correct the x values, then this time your guess is much better. Now this process of guessing is done by something called as an iteration matrix. If you pick up any standard linear algebra textbook, you should be able to figure this out. You take this iteration matrix and then you keep on doing this process till that particular equation is solved. Now there are three methods: Jacobi, Gauss-Seidel, and SOR. In general, Gauss-Seidel and SOR are much faster, but Jacobi can be parallelized very easily, meaning you can implement the algorithm on more processors fairly easily. Now, what are some of the pros and cons of the standard algorithms? One is that the solution procedure mimics the physics and the solution flows from cell to cell. So this is going to be very useful because when you have an initial condition, when the results are smooth, it's kind of guaranteed that the results that you get during the next iteration will also be smooth. The other advantage is that computing these iterations are very, very cheap. You can do them fairly easily. What are the cons? And as far as cons are concerned, the process is very slow, so the algorithm takes a lot of time to converge. And typically, if you take compressible flows and incompressible flows, right, solving that pressure Poisson equation is the most time consuming part, right? For example, if you take incompressible flows, the pressure Poisson equation is going to take a lot of time to solve, right? In that case, if you use Gauss-Seidel, you will still get the answer, but it's going to take a lot of time to converge. And the other thing is, it's not guaranteed that you will actually get a converged solution. Now, there are some criterias. Your spectral radius should be less than 1 for the iteration matrix, and this condition sometimes might not be satisfied. So what are the other alternatives? The other alternative is something called as the Krylov subspace method. Now, these are advanced linear solvers. The idea here is that you have a Krylov subspace, which is basically a vector spanned by combinations of a times b, a square times b, and a power r minus 1 times b. This might be a bit confusing for you. Usually you need to have intermediate level knowledge in linear algebra to understand this. But the key point here is, using this subspace, you can actually compute the inverse of a matrix. Now remember, if you have Ax equal to b, if you're able to invert the matrix A, then you can actually solve for x, correct? Using the Krylov subspace, computing the inverse is straightforward using the Cayley-Hamilton theorem, right? And hence, solution to Ax equal to b can be approximated. Alright, now there are three methods that are based on Krylov subspace. One is the generalized minimal residual method, the biconjugate gradient method, and the biconjugate gradient stabilized methods. So what are the pros and cons of this method? Pros is that it converges very rapidly, and convergence is guaranteed for a huge variety of problems. And as far as the cons are concerned, sometimes you might run into convergence issues during the first few iterations. And individual iterations are quite expensive to compute, which means the computational cost for each and every iterations might be a lot, but in total you are performing few number of iterations. So what is the general recommendation? For most flows, using SOR is fairly sufficient, right? If your Courant number is less than 10, then what you can basically do is you can end up using SOR. Now, if you're solving problems where the Courant number needs to be larger, greater than 15, in those cases, using Krylov methods is probably the best option because it's going to help you get the solutions in a very quick manner. Now, in addition to this, there is an option called preconditioning. I won't go into the details of it. Preconditioning helps in convergence, and that is basically used in conjunction with the Krylov methods. And that is used when your CFL number needs to be really, really high, something like 30 or above. And then there is another method called as Algebraic Multi-Grid method, which basically solves your linear systems in different grids, where you go from finer grid to coarser grid and coarser grid back to finer grid. When you cycle your iterative solver through this particular process, you can converge much more quickly. Again, Algebraic Multi-Grid method, also called as AMG, and preconditioning are intermediate to advanced level topics in linear algebra, so I won't be discussing them further. But the good thing here is that Converge and pretty much any other software automatically makes sure that it's providing you with the right set of parameters for the right type of problems that you're solving. Alright, so with that, I would like to conclude this lecture, and I'll see you guys in the next one. Bye.